some catching up to do today. I'm trying something different today. I'm gonna try to broadcast from my iPad so I can actually write. So if there are problems, just let me know. I'll give it a couple more, a minute maybe. Okay, so let me close my door, hold on. Okay, so as everyone knows, the assignment 1 is due today, so don't forget to send it. Just an email or a message on Slack would do. I know some of you already did, so thank you. Let's begin with just a very quick set of announcements. Let's see, share my screen. So let's just make sure we know where we are. So first of all, everyone hopefully can access these, the website, and the announcements are here. So this is probably the most up-to-date one. I'll certainly try to mirror this on Canvas. So for example, I posted the link to this really useful DOE, Department of Energy webinar. So these are just extra resources, so feel free to attend as you are able to. Okay, so since we had to cancel class on Tuesday, today we're going to catch up where we were supposed to, which is the solar radiation. Oops, I got to make sure I admit everybody. So the basics of solar radiation, the lecture notes are already posted here, and we'll go through that today, and then we'll get started on the introduction to non-imaging optics. Part 1, we have to divide this into 2 lectures. And assignment 1 is due today. And just keep in mind, the assignment 2 is due next Tuesday, and we'll talk more about it kind of halfway through today's lecture. Okay, before I begin, are there any questions? Everyone's okay? It's a little hard for me to monitor the chat, but so if you do have questions, just make noise. Okay, I can't even see your videos easily because I'm trying to use 2 different monitors. Yeah, so just say something if you have a question, okay? And Apratham is here, so he'll monitor the chat, some of it, but just in case. Okay, can you see my video? Yes, I think you can. But, all right, let's get started. Sorry, it's crashing. Okay, here we go. So today we want to start with something fairly basic, understanding of sunlight. So the focus of this class is optics for energy, and of course the main source of energy for us. Whoops. Sorry about this.
Your audio is breaking
why I
up.
guess you shouldn't be late. Oh, okay.
I don't know, is it just on my side? Or?
I'm on a wired Ethernet, so it should be pretty good. But does anyone else hear me okay?
It's breaking up for me also.
Okay. So maybe it's my headset. Right. Let me see if I can make it a little better. Okay, hopefully that works a little bit better, but let's continue. So today we want to talk a little bit about some basic understanding of light and sunlight in particular, because we're going to deal with this quite a bit during this class. First of all, of course, we know sunlight is the source of all Earth's energy. It produces heat and food. As this converts light energy from the sun into stored potential energy or chemical energy, which is then converted into food. And of course, fossil fuels, even fossil fuels can be thought of as stored solar energy from millions of years ago. So everything is eventually related to the sun. Biomass converts solar energy to fuel, which biomass, as we talked about in our first lecture, refers to dead trees and organic matter. Wind energy also is a result of solar in the sense that air is heated, and because of Earth's rotation, there's wind that flows one place to another because of changes in pressure. So it can also be traced back to sunlight as well. And of course, hydropower is generated by the sun in the sense, as we talked about in the last, in 2 lectures ago, evaporated water returns to Earth, fills a dam, for instance, and runs, and when you open the dam, runs a turbine. So everything is, in a sense, related to the sun. So we'll think a little bit more carefully about, what properties of sunlight are critically important. But we need to understand some fairly fundamental ideas of light itself, primarily the electromagnetic spectrum. And this is very critical because the light we receive from the sun actually spans a very large portion of the spectrum. Okay, let me weigh in as well. So try not to be late. Okay, so light itself has many properties that are of interest. For us, for this class, we'll focus on a few, particularly wavelength. So this notes the wavelength is increasing in this direction, where it goes from gamma rays, which are very high energy, very short wavelength, X-rays, ultraviolet, visible, which is of course what's most interest to us, which has a wavelength of about 10 to the minus 6 meters, infrared, microwave, radios, and so on. Of course, radios are also pretty important. Visible is most important to us because this is the majority of energy we receive from the sun is in the visible. And this is, by the way, why human beings evolved and most animals evolved to be able to see in the visible light. And that's represented by the wave here, where you can see that this the spacing between the peaks of this, which represents the wavelength, is actually getting shorter as you go from left to right. Now, the wavelength is inversely proportional to frequency. Okay, nu is frequency, which is represented as hertz, which is number of cycles of electromagnetic waves per unit time. Okay, so as wavelength is increasing from right to left, frequency is increasing in the opposite direction, from left to right. So you can see that the gamma rays have the highest frequency here, and the radio waves have the lowest frequency here. Okay. Now, this, of course, we all know, if you focus into the visible part of the spectrum here, the violet, which is over here, which is, let's say, around 400 nanometers in wavelength, has the highest frequency. And here, the red, let's say around 650 nanometers in wavelength, has a lower frequency. So wavelength is increasing, frequency is decreasing. Okay, this is important to understand. Now, we'll relate this to energy shortly. Now, this is the wave picture of light. Of course, in quantum mechanics, we know that there is a particle picture of light as well. So in modern physics, where the light exists not only as a wave, and when we say a wave, we refer to the electromagnetic wave. What does that mean? That means there is a disturbance in space and time, by the way, but let's ignore that for the time being. A disturbance in space of the electric field, which is varying in time. And when the disturbance is varying in time in the electric field, that causes a disturbance in the magnetic field. And the variation in the magnetic field, both in space and time, creates a disturbance in the electric field, and so on and so forth. So there is this combined variation in both electric and magnetic fields, which creates a sustained propagation of light. And that's what the wave theory is. Okay, this is Maxwell's wave theory, about several 150 years old or so, something like that. And here we define the light in terms of wavelength and frequency, as we just talked about, lambda and nu. Okay. But light is also a particle, which we have realized for about 100 years because of quantum theory. And the particle of light is referred to as a photon. Okay. And here we define, in the case of a particle, like a soccer ball, for instance, it has momentum and energy. Now, these things can coexist, and in reality, they do. Of course, this is not a fully resolved situation. In physics, there's still quite a bit of interesting work happening into understanding what does that really mean. So the description of reality, of course, is still a little bit up in the air, but from a mathematical perspective, this is the way we need to think about it. Now, why are we talking about this? We are talking about this because we're interested in energy, and energy of light can be represented by this equation, E equals h nu, where h is the Planck's constant. We'll see this quite a bit shortly. And it's given by, and because nu is related as c over lambda, you can see that these equations are equivalent. H nu equals hc over lambda. So you can see as lambda increases, nu decreases. Now, you can see that also that the energy is directly related to nu, which means that as nu increases, energy increases and wavelength decreases. So this is kind of a fundamental thing to keep in mind. Now, what are the important characteristics that we are interested in for the purposes of this class? One is the spectral content of incident light. Now, what does that mean? That means how much energy is present in light as a function of lambda or nu. Of course, we know they're equivalent. What does that mean in practice? What is the color of the light? Is the light more blue? Is it more red? Is it more green? And this is important because blue light contains different energy than red light. Okay, so we need to understand the spectral content of the light that we're dealing with. Next, we need to also understand what the radiant power density is, and we'll talk a lot more about this going forward, but essentially it's how much power is spread among all these different colors. Next, we're also interested in the angle at which the incident light strikes an absorber, and of course we saw this in the case of, for instance, the solar parabolic concentrator, right? So if you have light coming in at an angle, so we know a parabolic concentrator will concentrate the light like that. But if I come in at a different angle, I will miss the focus. So it will simply go in all different directions. So this direction in which the light's coming in is quite important. Okay. And of course, because we are primarily interested in situations where we're collecting light over a certain time, we also need to understand, okay, what's the amount of energy that's coming in the case of from the sun throughout the year in the case of seasons and things like that. Okay, so fairly basic stuff. Now, as I said before, Planck's constant defines the energy of a single photon. So this is the, oh yeah, it's there, sorry. So this is the energy of one photon, keep in mind, okay? And this is Planck's constant. The key thing to keep in mind is that it's a very small number, right? 10 to the minus 34. So the amount and the units, let's also keep in mind, joules times seconds. Okay, so you can see, by the way, a very useful thing to keep in mind is that if I take h multiplied by nu, and h units are joules times seconds, multiplied by units of seconds, right? I will end up with joules, which is of course the units of energy. So from a dimensional perspective, you may want to check that your equations are correct. Let me let Nick in. Okay, so this is a good practice, for instance. It's also, for instance, you can also check dimensionally hc over lambda, right? So h is joules seconds, c is meters per second, and divided by wavelength is meters. So my meters cancels out, seconds cancels out, I still get joules. Okay, so everything dimensionally makes sense, which is important. Now, because these numbers are really small, typically you express the energy in terms of electron volts as well. One electron volt is the energy required to raise an electron through a 1 volt potential. Of course, we know in the case, if you look at an energy band diagram, if you have an electron which sits, this is referred to as a valence band, and this is referred to as a conduction band. Oh, sorry, the opposite. It's the conduction band, that's the valence band. If I have an electron which is here, and I push it up the hill here, the amount of energy, and this difference is 1 volt, the amount of energy, the amount of work I have to do to push the electron up here is 1 electron volt. Okay, and 1 electron volt is simply given by this number, which is again a natural universal constant, because the charge of an electron is fixed, and this is simply the charge of an electron, 1.6 times 10 to the minus 19 joules. Okay, now we need to think about some terms that we need to understand, because we have to speak the same common language when we think about you know, how to analyze and design energy-related optical systems. So one is the first and probably a simple thing to understand is something called photon flux. Photon flux is defined as the number of photons per unit time, so per second, per unit area. So again, it's the number of photons per time per unit area. So you can see that the units have to be per second and per area, right? And it's a number. So of course, this makes sense, shown here. This determines the number of so for instance, if I have this many photons, let's say I have 1,000,000 photons coming per unit time per unit area onto my photovoltaic cell, and if my photovoltaic cell has 100% efficiency, every single photon that comes in is converted into an electron, so it produces current, I can say, okay, I'm going to get 1,000,000 electrons per unit area per unit time. So that's what this determines, for instance, the number of electrons generated in a solar cell. And we represented it, this quantity by the capital phi. Again, number of photons by time per area. Okay. Now, the photon flux by itself doesn't give enough information on the energy, right? So here, if you look at what I said, this is just simply the number of photons. If I don't tell you what type of photon it is, what is the frequency of the photon, I don't know how much energy has come through. I only have the number of photons. Some photons have more energy than others, as we just talked about, right, by this equation. So the photon flux by itself doesn't give enough information on the energy. So to compute energy, you also need to know one more thing, one more piece of information, which is the wavelength of the photon or the frequency of the photon. So let's do a quick example. The power density, which is power density. Now power is energy per unit time, right? So it's simply joules per second. Power density is, density refers to area. So this will be joules per unit time per area. Okay, so power density and joules per second is watts, right? So we know this is watts, so I can write this as watts per unit area. And that's what this is, okay? My power density, H, is simply the flux, which is capital phi, times the energy per photon, which is hc over lambda. So again, let's think about what it's saying. If I have 1,000,000 photons coming into a system, and each photon has a wavelength of lambda, I can take, so 1,000,000 photons per unit time per unit area, then I can take the energy of each photon multiplied by the number to get the total power per unit area getting into the system. Now, power already is per unit time, so I don't need to worry about that. So another way to think about this is the amount of energy per unit area per unit time entering a system. And of course, this is wavelength dependent. So if you have a different color of light going into a system, that will have a different power density. Okay, now I want to take a minute and I want you to answer this question. Again, I'm going to put you all in breakout rooms and give you maybe a minute and a half or so to answer this. But let me read the question. If a red beam has the same power density as a blue beam, which beam has higher photon flux? Okay, so imagine I have a red laser pointer. I'm going to point this at a solar cell. I'm going to take a blue laser pointer, point it at the solar cell. Actually, let's ignore the solar cell. If I have a red laser pointer, I'm going to count how many photons are there per unit time, per unit area. I'm going to take a blue laser pointer, same power density. I want to count how many photons are there per unit area, per unit time. Which one has a higher photon flux? Which one has more particles? Okay, give me a second because I have to use the other computer to put you in a breakout room. Okay, 1 second. Ah.
Hello? Hello?
Okay.
So I think some of the students have problems with their internet. Is there anything we can do about that? I think on their side is what they're saying.
Let me see. I don't think there's anything I can do. I guess the only thing we can say is, so certainly you'll be able to watch it later. Yeah, I'm not sure I have much control there. I see a few students actually are not able to come back. Did the breakout rooms work, by the way? Because sorry, I had some technical issues. So
They worked for us.
Yeah, so the one I was in worked, yeah.
okay.
But the student who was there was saying that he couldn't follow the lectures this class at all because his internet is really poor.
Yeah, it's nothing I can do about it except that if you talk to him, let him know that it'll be recorded and posted.
Yeah.
So, so I'm going to ask, is there a volunteer for an answer?
I can do the answer.
Go ahead.
We got that red has the higher flux because it has the wavelength. It's higher, so red will have. So yeah.
Okay, so lambda red is higher than lambda blue. That is correct.
Yeah.
So the frequency of red is smaller than the frequency of blue. The energy of red is smaller than the energy of blue. Is everybody okay with that? Because we know that the energy is directly proportional to wavelength, inversely proportional to wavelength and directly proportional to frequency. So if I draw a red photon has less energy than a blue photon. So if I have to have the same power density, I need to have more of the red in order to have the same power density. Does that make sense? So it's like saying, okay, I need to have 10 of these or 8 of these versus just 4 of these to produce the same power. Okay, but of course, this is something you have to think about, but just keep in mind, this is very important, because also keep in mind that if I only have 4 photons, I'm only going to generate 4 electrons, right? If I have 100% efficiency. And here I'm going to generate 8 electrons. Now, even though the power density in each case is the same, I'm generating higher number of electrons. Now you might ask, okay, does that mean I'm gonna get higher current? In an ideal world, yes, except that this higher current produced by the red will come at a lower voltage, as we will see. So the power which is given by current multiplied by voltage is still the same. Okay, so the current is higher. For the red, the current is higher, but voltage is lower. For the blue, the current is lower, voltage is higher. So everything matches up. Of course, this is in the ideal world. In a real world, of course, every photon is absorbed with a slightly different efficiency, so it doesn't quite work that way. And we'll come to that later on. But I just want you to intuitively understand that these things are important. Okay, so now that we appreciate that the wavelength is actually a very important property, we need to understand, okay, how do we measure this? How do we plot it? Okay, so we express the dependence of wavelength by something called spectral irradiance, which is power density as a function of wavelength. And it's shown, for example, in this plot at the bottom. The horizontal axis is wavelength. In nanometers, it goes from 300 to 800. So visible is, something like a human can see something in this range. Okay, if you are younger, you can see a little bit in there as well. And on the vertical axis is what's called irradiance, which is in watts. I'm going to write it down here: watts per meter squared per nanometer. Okay, units are important. What does that mean? As you can see, this is power density, watts per meter squared. Per nanometer refers to per unit wavelength. So here it tells me, okay, if I look up here at 400 nanometers, I have 2.2 whatever, 2.3 watts per meter squared per nanometer. Okay, now how is this useful? Of course, in real world, we need to know all the wavelengths, right? Let's say I'm going to collect this much of the light, say 400 to, let's call it 600. Then I need to be able to measure, I need to integrate all the energy within this curve. Okay, so here I would take this value F and integrate it. It's a function of wavelength. Now, once I integrate it over wavelength, I'll get power density, watts per meter squared. Okay. So spectral irradiance, also represented by this F, is simply H divided by lambda, or if you want to do it in a continuous case, F is also more precisely defined as the derivative of H with respect to lambda. So it's how the power density varies with wavelength. So as I said, if you do the integral, you get the total power density back, right? So this is H. Of course, for simplicity, we'll just write it as a discrete term right here, which is good enough for many applications. And of course, you can plug in H is phi divided by HC over lambda, and that's where you get the second part of the equation. Okay. So again, keep in mind that the spectral irradiance is now dependent on wavelength. Now, remember Planck's constant H and the speed of light C are both constants, right? They're universal constants, they don't change. Of course, the speed of light can change in some materials. We'll come to that later on, but let's put that aside. For now, they don't change. So the only thing that depends upon is the wavelength of light, as we know, and the phi, which is a flux. Okay, so how much power? So this example shown in the bottom here is a xenon lamp, the spectrum of a lamp, for instance. Okay, now the next term we need, and the term, actually this is the same term we just talked about, radiant power density. It's also called spectral irradiance, just to confuse you. There are lots of terms here, and some of these are historical. But from your perspective, you just need to understand what these terms mean, okay? So radiant power density is defined as the total power density emitted from a light source, and it's calculated by integrating the spectral irradiance over all the wavelengths of interest, which we just talked about, right? F of lambda, d lambda, integrate. Now, I have a quick question here. What are the units of H? I'm not going to do the breakout rooms, but I want you to take 60 seconds and work out yourself what the units of H are. And
I thought it was just watts.
Sorry,
yeah, I thought it was just watts per meter square, right? Like power density that you mentioned.
That's right.
Let everybody think about it for 30 seconds or so. And then we'll talk. We just discussed it, but I want people to kind of think from a dimensional perspective. Okay, you're correct, but the reason I'm asking is because sometimes it's useful to associate terms with actual physical dimensions. So okay, so how do we do this sort of a problem? Of course, d lambda is in nanometers, right? And F we just talked about. This is watts per meter squared per nanometer. And you do the integration, what you end up with is watts per meter squared. So you're absolutely correct. What is H? This is simply power density. Okay, hopefully everyone's okay with this. Okay, now we need to know something fundamental regarding radiation, something called the black body radiation. This is important, for instance, for many reasons. But for example, the reason we may want to understand this is if you want to design, let's say, a solar cooling system or a solar desalination system, in order to understand how much power is coming into the system and what you're going to absorb, you need to understand what a black body is and be able to model it, okay? Now, what is a black body? Black body is an idealized version of an object that emits and absorbs light, which is everything, right? So this is a highly idealized model, but for many light sources, such as the sun, incandescent lamps, and many other things, black holes, for instance, all of these can actually be mathematically defined as a black body, and they can be modeled as black body emitters. So an ideal black body absorbs all the radiation incident on its surface and emits based upon its temperature. Now, that's very important. What does that mean? An ideal black body absorbs and emits radiation based only upon its temperature. It doesn't matter what the shape is. It can be a cube, square, a sphere, a pyramid, doesn't matter. Doesn't matter what if it's textured, if it's smooth. Okay, so this is a very foundational concept. And it comes from thermodynamics, the first law of thermodynamics, actually, and quantum mechanics. So spectral irradiance is actually governed by something called the Planck's radiation law, which is defined here mathematically. Again, this is the term we just saw, watts per meter squared. Okay, it's defined by some complicated equation, but most of the stuff are constants, right? 2 pi, h is Planck's constant, c is the speed of light, c squared. Of course, this is not a constant, that's the wavelength, lambda raised to 5. And then there's this complicated exponential term at the bottom here, which is where temperature comes into play. So this is the key thing we need to keep in mind, as well as lambda. Everything else are constants. Now, K is a constant we haven't seen before. We'll see this shortly. It's called the Stefan Boltzmann constant. Sorry, this is called the, actually now I forget the name of it, but we'll talk about it shortly. Okay, but it's a constant. Okay, so the only thing that the equation depends upon is temperature and wavelength. Now we can plot this, and temperature here is modeled in kelvins, not degrees. Okay, and kelvins means that there is no negative temperature. 0 is the absolute lowest temperature, which is the ground state of any quantum system. Now we can plot this radiation. Now from this spectral density, power density, you can plot this curve, which is shown on the right here. Okay, sorry, on the left here. This is wavelength, and this is intensity, and this is an ideal black body radiation. And of course, there are many curves based on temperature. So the hottest curve is shown here, which is roughly the temperature of the surface of the sun. You see this plot. As the temperature goes down, you see the plot actually goes down, as you can see. But it also, the peak of the plot also shifts to the right, goes to longer wavelengths. Same thing here. Okay, so two important properties. One is that the intensity itself is going down as things cool, but it also shifts to the right. And these things here refer to the surface of the sun, the carbon arc lamp, and the incandescent lamp filament at 3000 Kelvin. And this plot is simply coming from this equation here. Now we can, of course.
Can I ask a quick question? So like it seems like the unit of F is watts per meter square as well.
Yes.
As you wrote beside it. So I assume F and H are kind of like interchangeable since the unit of H is watts per meter square as well.
Actually, let's make sure. I messed up. So there should be a nanometer as well. So I'm going to cancel that and write this is watts per meter square per nanometer. Okay. This is spectral irradiance, so per little sliver of wavelength, which is exactly what we talked about here, this F. But good catch, yeah. I made a mistake there.
Oh yeah.
Now, of course, to get H, all you have to do is do the integral, which we just talked about, right? And in this case, you're integrating over all the wavelengths, so 0 to infinity. And if you do this integral of this complicated equation, you get a very simple expression, which is referred to as the Stefan Boltzmann law. H is sigma T raised to 4. This is a very, very nice, because what it's saying is that the power density here, which is watts per meter squared of a black body, is only dependent upon T. Sigma is a constant shown here called the Stefan Boltzmann constant. Okay, it's a very important result because that means you only need to look at the temperature of a black body to know how much power it's emitting per unit area, per unit time. It's an approximation, but it's a good approximation for instance, for the sun. Now, the units here are also important. You can work this out to see if they make sense, right? This is joules per second per meter squared per Kelvin raised to -4. Now, temperature is kelvins. So if you cancel this last term out, you'll get joules per second, which is watts per meter squared, as expected. Okay, so the units all make sense. Okay, now let's think about this a little bit more detail. The wavelength where the spectral irradiance is maximum. So which is this point here. So coming back to this curve, you see this point here, which is the peak of this curve, peak of this curve, peak of this curve, peak of this curve, which follows this dashed line here, right? So you can see as the temperature decreases, the peak of the curve goes to longer wavelengths, okay? And this is also a fundamental property, and you can actually prove this. And it's very easy to do, by the way. So you can simply take Planck's radiation law, which is shown here, and we know from calculus, if you take the first derivative of it with respect to lambda and set it to 0, you'll find the inflection point, which is the maximum point, right? I'm not gonna have you do it, but it's relatively straightforward. You can do it, and you'll end up with a very simple expression, which is called Wien's law, which is the peak wavelength is now some constant, in this case 2900, divided by T, temperature in Kelvin. So of course it's inversely proportional to T, which makes sense, right? Here we saw that the curve is going down like that. As temperature increases, it decreases. So the lambda peak is inversely proportional to temperature. Okay, so the temperature of the black body affects both the spectral distribution, so the shape of the curve. As you can see, the shape is changing as temperature decreases, but also the peak of the curve. Okay, and also the integral under this curve is the h, right? This h, and that's also changing. As we know, it's very sensitive to temperatures, T to the power 4. So let's look at this picture here, which is a picture of the night sky showing two different stars, Rigel and Betelgeuse, and this is the Orion Constellation. And the question is, okay, by looking at this picture, can you tell me which star is actually hotter? And don't shout out the answer yet. Let's give everybody, let's say 10, 15 seconds or so to think about this. And think about how it's relevant to what I just talked about. Okay, now you can, someone can shout out the answer.
The blue is hotter.
And why?
Because the wavelength of blue, it's smaller. So if you do like temperature equals 2900 divided by the wavelength, then you can do, yeah. Then you, yeah.
Correct. So you can see that Rigel is actually much hotter than Betelgeuse. And this is actually very important because this is, for example, how we look at distant interstellar objects and look at their spectral signatures to understand their properties. Not just temperature, you can make other inferences as well, but it's a very simple idea. Now, we'll come back to this concept again. For example, if you were a lighting optical designer and you wanted to design the headlamp of the latest Mercedes car, like, you may want to think about, okay, what should my spectral distribution be, right? And we'll talk about this problem soon. And this is a very real problem, right? If you're trying to design and you have access to all kinds of LEDs and lasers and so on, right? So probably you have to think about this. And not in that case, it's not temperature. In that case, it's really like what's the visual acuity of a person. Just realized my battery is low, so I might have to go to my laptop if it gets shut down. But okay, so the details of the sun itself are also important. Sun is a hot sphere, as we know, whose internal temperatures reach over 20 million Kelvin. Actually, I'm gonna see if I can, whoops. Let's see if I can turn off the blue. Oh, I can't, never mind. Sorry. Okay, so if it shuts down, give me a second, I'll connect on my laptop. The internal temperature of the sun reaches over 20 million Kelvin due to nuclear reaction in its core, which essentially takes two hydrogen atoms and fuses them to form helium. So if you look at the details of the sun, it's fairly complicated, and a lot of it we still don't know because we haven't actually sent spacecraft to, especially to the poles out here. This has never actually been seen by humans, but there are lots of interesting projects where people are trying to do it. But in any case, inside of the sun, there's nuclear fusion, and then there's convection. So there's lots of energy which are generated in this core, and then the whole thing is so hot that this material is now in the form of plasma, so which is basically like a gas. So there's convection, that's heat taking the heat out to the surface. So this is millions of degrees, but at the surface, it's more like 6,000 Kelvin, something like that. Okay. So the radiation from the inner core is absorbed by hydrogen ions closer to the surface. So the hydrogen ions are essentially squeezing, fusing to become helium at very, very high temperatures. And then because of radiation and convection, the sun's surface is about 6,000 Kelvin. And total solar radiation now resembles a black body at about 6,000 Kelvin. If the total power emitted by the sun is the power density times the surface area of the sun, it turns out to be a pretty large number, 9.5 times 10 to the 25 watts. Okay, well, we'll come back to that number later on. The other thing to keep in mind is that the solar radiation spectrum, the color of sunlight, changes where we measure it. At the top of the atmosphere in space, you get the purest form of solar radiation, which is shown in yellow. As you get, and that's roughly modeled by this black body, but as you come into through the atmosphere, there's lots of absorption that happens, which causes these sorts of dips and so on, and then you end up with this red plot. So if you're building solar devices, solar photovoltaic devices, for instance, for space, you will think about the yellow plot, whereas if you're doing this for terrestrial applications, you'll look at the red plot. Okay. Again, solar radiation in space. So for instance, if you're building solar panels or concentrators to be used in Mars or on spacecraft and so on, you have to think about this slightly differently. So for that, the solar irradiance on an object some distance d from the sun is found by dividing the total power emitted from the sun divided by the surface area over which the light falls. So sun is emitting in all directions, but if you are at the Earth here, you will see a certain amount of energy, but if you are over here, you will see a lot less energy. And because it's far, not only because it's farther away, but because it's also spread over a larger area, right? But you can estimate this pretty easily, as shown by this equation here. Again, the flux density, power density, sorry, is given by sigma t raised to 4, right? Stefan Boltzmann Law. And all you need to do is scale by the distances. So this is the radius of the sun squared divided by the distance from the sun squared. So if you're at Venus, you'll see a radiance of 2,611 watts per meter squared. If you're on Earth, you'll see 1,366 watts per meter squared. If you're at Pluto, it's very slow, 0.878 watts per meter squared. So it really matters. Of course, the distances are very vast, right? We're talking about billions of meters here. The actual power density also changes as Earth moves in its elliptical orbit. This is very important, especially if you're building terrestrial systems and also in some space systems as well, right? If you're a spacecraft that's trying to go through the solar system, then it matters how far you are from the sun. So, and while you're on Earth, of course, in July, you are farther away from the sun than in January, for instance. So you have the seasonal variation as well. And of course, it also matters what hemisphere you are and so on. And you can model all this very nicely by a fairly simple equation as shown here. and this is only for the purposes of your knowledge. For our class, we will ignore this level of detail. That's something you should be aware of. Now, in the case of all energy applications, we have to use standard spectra because the actual spectra changes where you measure it. So this can change from place to place, altitude, Salt Lake City versus sea level. So we have to use some standards in order to be able to make actual products like solar cells, solar concentrator, and so on. So there are standards which are shown here. For instance, AM0. AM, by the way, refers to air mass, as we will see shortly. AM0 means it's out in space. There's no air mass. AM1.5 means it's on Earth. And there's something called direct versus global. Direct means the sunlight is coming straight. Global means there is some diffuse light as well, which is where light is scattered by clouds and water vapor and so on. And there are some small differences in spectra. So for very detailed analysis, you need to know this stuff. And we'll talk more about this as we talk about some specific examples. Now, solar radiation on Earth is different than that's on space. And the reason for this has to do with many factors, and you should be aware of what these are. The solar radiation incident on Earth's atmosphere out in space is very constant, but the radiation on the Earth's surface varies widely due to atmospheric effects, local variations in the atmosphere, such as water vapor, clouds, pollution, etc., latitude of the location, season of year, and time of the day, of course, right? The parameters that change that are important for us are spectral irradiance, the power density, and the angle of incidence. All of these are quite important. And the atmospheric effects are modeled here. This is a nice graphical representation of what happens. You come in with 100% of the light. Some of the light gets scattered to the Earth, which is shown by this purple line. Some of the light gets scattered back to space, and some of the light is simply absorbed, as shown by these small red lines. And all the different mechanisms are here. And what you see is that roughly 70% of the light makes it down to Earth, which is direct, not scattered. 7% is scattered by everything else. Of course, this can change depending upon if there's inversion, for instance, in Salt Lake Valley, right? That can change the scattering of light. So these things can change with time, but this is a good rule of thumb to keep in mind. And of course, certain wavelengths scatter more than others. As we know, the sky on Earth looks blue, but if you are on Moon, it looks black. There's no scattering, right? And the reason is, of course, the particles scatter with a very high sensitivity to wavelength. So blue scatters a lot more than red. The other things to keep in mind, there are high absorption at certain wavelengths, so photon energies are close to the bond energies of certain gases, primarily ozone, carbon dioxide, and water vapor. So you end up with these very sharp dips. An example is shown here, right? Here, here, and so on and so forth. Those things are, sometimes important. Far infrared light, which is wavelengths larger than 2 microns, is absorbed by water and CO2. UV, which is less than 300 nanometers, is absorbed by ozone, but of course, not enough to prevent sunburn, so which is why people have to wear sunscreen. And these cause these deep troughs in the spectrum. Dust and air molecules absorb across the spectrum as well as scatter light, so they reduce the overall light. Now, it's useful to keep in mind when the sun is overhead, all wavelengths are uniformly absorbed and sun looks white. Whereas during the morning and evening, the optical path is longer, the light from the sun has to pass through a larger thickness of the atmosphere, and shorter wavelengths are more effectively absorbed. Shorter wavelengths mean bluer light, so red passes through and the sun looks red, right? So it gives a red color. And because the shorter wavelengths are scattered, which is the blue light, that light gets scattered from the rest of the atmosphere and reaches the eye, which gives the sky the blue color. And of course, we know we need to track the sun during the day if you have a concentrator. And we'll talk a lot more about this. But the key point in this graph down here is to show that if you're at the equator, you have a very different curve of this is energy as a function of the time of the day, as opposed to when you're further away from the equator. The farther you go, of course, you're at a larger angle with respect to the sun, depending upon the season, of course, as well. Which is why when you install solar panels, of course, we need to point it south when you're in the northern hemisphere. If you're in the southern hemisphere, you'll point it north. And we'll talk more about it. As I said before, there's a difference between direct and diffuse sunlight. Diffuse light is because of something called Rayleigh scattering in the presence of clouds and water vapor and so on. Shorter wavelengths are scattered much more than the longer ones, which is why the sky looks blue. 7 to 10% is diffuse light. Now, why is this important? If I, for instance, have a parabolic concentrator to collect sunlight onto, let's say, a hot water system, if I have direct sunlight, which is coming straight, this is not a problem. I can focus it, no problem. But diffuse light means that I'm coming at all kinds of angles. The angles are not well controlled, it's random, which means that I'm going to lose all of that because it won't be focused. Okay, so this is why it's important to understand the difference between diffuse and direct, which also means that if you have a cloudy day, you won't concentrate as much of the light. And this, by the way, is dictated by the second law of thermodynamics, as we'll see. So it's very, very important. Atmospheric effects are related to something we just talked about, air mass, or AM, which is the amount of mass of the air through which the light has to pass. So for instance, the sun is directly overhead, it passes through less light, air, as opposed to when it's slanted, right? You can see very clearly. And the air mass is defined by 1 over the cosine of the angle with respect to the vertical. So the larger the angle, as theta goes to 90 degrees, 1 over cosine theta goes to infinity, right? So you have to go through a very large amount of air. And you can also model this more carefully, which takes the curvature of the Earth into account, as shown here, which again is only there for your information. We won't use this for our class. You can also define the direct component of the sunlight as a function of the air mass, as shown here, and how it changes with altitude, which is of course important for us in Utah. So higher altitudes, you have higher irradiance. So also keep in mind, even on cloudless days, roughly 7 to 10% of the light would be in the diffuse component. So that's not much you can do if you need to collect only the direct component. Okay, so at this point, I want to take a short break and talk about the assignment 1, which is due on Tuesday. First, I want to stop and make sure there are no questions. And I can't watch my video while I have this on, so I'm going to rely on anyone to say something if you have a question.
Is it assignment 1 or assignment 2?
You are correct. This should be 2. My mistake.
It's okay.
Sorry. This week has been a little crazy for me, sir.
For all of us.
Mistakes. Yes. So yeah, 2. So one quick piece of advice about what we just went through. It's important, again, I don't need you to memorize any equations. That's not the purpose of this class, but I would like you to gain intuitions, like understanding of what we talked about. So make sure you go back and review this stuff and think about it, okay? And of course, ask questions on Slack if you have them. Okay, I'm gonna talk about this and give you maybe a minute or 2 break. But so let's, first of all, not everybody has completed assignment 1, which is due today, so make sure you do. If you do have an excuse, for instance, you don't have internet or something, just let me know. Of course, it's flexible, right? But if you don't let me know, then I don't know. So just let me know. Okay, and assignment 1 is very simple, right? It's just not much to it. Okay, assignment 2, what do you have to do? You have to do something like roughly 10-minute presentation in class. It's a team presentation, so you'll be submitting 1 video or making 1 presentation. But it'd be nice if you're able to split the job among your teammates, but I'm leaving it completely up to you. You can have 1 person presenting it, or all of you can take turns presenting, whatever. Okay, just make it very clear. And online students will submit a video. Typically, it can be a screen recording with the audio of their slides. Okay, what's the objective? What are we trying to do? First, we want to become familiar with our project topic. This is the main goal. What does that mean? That means we want to understand what people have already done. Okay, specifically, you already done this. I'm going to skip that. What are the main products or solutions that exist today? So for example, if you're talking about solar desalination, it's very clear, okay, what are the existing products? And it can be products that are using fossil fuels. That's fine. That's an existing solution, right? If you're talking about daylighting, look at what are the products out there. 3M, for instance, has a multi-billion-dollar market share in the daylighting industry today. The next point is very important. What are the main challenges generally in the field? Could be the cost of fuel is too high for desalination. That makes the water too expensive, right? I'm just giving rough examples, but it's up to you to identify them. I would try to identify, like the top 3, for example, problems. And the reason I'm saying this is because I want you to come back when you do assignment 3 to propose solutions to these problems. Doesn't need to be these problems, but it will be nice if it can be consistent. So that way you've thought about it, okay? And finally, the last point is compare the advantages and disadvantages of the existing products and solutions. And here the goal is to really think about, okay, what are the problems that have not been solved yet? And you can start thinking about ideas to solutions or inklings of solutions to these problems, which will actually, of course, be part of assignment 3, so you don't need to do it yet, but I want you to start thinking about it. And again, add as much detail as possible, but of course you only have roughly 10 minutes, so include citations, websites, whatever you want to do. And of course, it'll be recorded. This research will inform your future assignments, so it's important that you do as thorough a job as possible. It's a little harder once you go down a particular road to change mid-semester. So that's why I'm giving a little bit of warning. And again, because there are 3 or 4 people in your team, I recommend that you be efficient and try to split your work. And this is part of the experience I want you to get out of this, is working in remote teams, being able to cooperatively produce something valuable, right? Which is, again, more valuable than the sum of each person's contribution. And again, I highly recommend using Slack for this. So at this point, I want to take a let's take like a 2-minute break. Let's make a Zoom. Okay. Great. Okay, I'm gonna grab some water. Oh, my iPad's not gonna die. That's good. Okay, let's all take a walk around, stretch your legs, take a 2-minute break. Let's say, yeah, roughly 2-minute break. I'm gonna put my timer on, so don't waste a lot of time. Okay. Okay, I'm gonna come back. Is my audio still problematic, or you guys understand what I'm talking about?
Sounds
I think
clear.
it cleared up. Yeah, it cleared
Sounds
up.
good.
Okay, good. I didn't do anything different, but at least I'm connected with a wired Ethernet, so Wi-Fi should be good. Okay, let's share. Okay. Oops. So the rest of the class is introduction to non-imaging optics, and I realize that we don't have much time, but we'll get started here. First of all, I just want to say I'm going to post a couple of useful resources on the website, so take a look at it. There'll be an interesting and useful review paper by the person who actually coined this term. His name is Roland Winston, who's a professor at the University of California, Merced. He's a fairly well-known physicist who actually developed quite a bit of the foundations of this idea called non-imaging optics. So I'll post that, and it's an easy read as well. Just a tiny bit of math. Okay, so let's review very quickly what is this non-imaging optics means, right? This is a little strange. What is that? Okay, so to understand what that is, we need to understand what imaging optics means, and which is what Apratham taught us last week. Okay, very nicely. So let's take a quick review. In imaging optics, what we are trying to do is we are going to take light from a single point P, and we're trying to collect it to a single point P prime. Okay, so light from point P is captured by the optics and imaged onto P prime. So this is a unique one-to-one mapping. So in other words, there is a point P prime that corresponds to P. And there's only one point P prime that corresponds to P. I cannot, if I take another point here, Q, it will not correspond to P, it'll correspond to a different point, sorry, Q prime, it will correspond to a different point, Q. Okay, so it's unique and it's one-to-one. In non-imaging optics, this mapping is no longer one-to-one. This is the key difference. In non-imaging optics, again, if you really think about what we're trying to do, is we are trying to take energy from a light source and direct it to a receiver. So the goal is to create a desired irradiance on the receiver for a given light source. There is no one-to-one mapping of the points on the source to those on the receiver. What I mean by that is if I take a point here, A, I can receive energy to A from many points anywhere over here on the light source. So it can be a many to one mapping. Okay. It's a conceptual take on this whole thing, but we'll make it a little more mathematical shortly. Oops. So again, if you think about an object, okay, which is shown here, and you have an optic, a lens, for instance, and you're forming an image. Rays from a point P, which is shown by these lines here, get collected, redirected by the lens onto a point, in this example, Q. So light from P goes to Q, light from F goes to A, light from E goes to B, and so on and so forth. Okay, and if it's a simple lens, we have a magnification M, which gives you that the size of the image here is equal to the magnification times the size of the object. Okay, we all know this, and also we know that the image is inverted. In other words, if I have an arrow pointing down, it'll form an image of an arrow pointing up. Okay, so these are basic concepts in imaging systems. If you think about how we design imaging systems with lenses, we design them with surfaces, typically, right? So we have a curved surface. We call this mathematically a Cartesian oval. So let's say we're only interested in imaging one point, P, and we want to make sure all the light that comes from P ends up at Q, okay? So Cartesian oval is a surface such that each point on it has only one ray of light from P. So if I take any point, for example, R, I have a ray of light from, I can draw a straight line from P to R, which represents the ray. And what the surface does, based on refraction and Snell's law, is simply redirect that ray to Q. Okay, and I can take any other point here, and I can do the exact same thing. So I change the shape of this surface such that this redirection happens. Now you can write this based on something called Fermat's principle or Fermat's law, saying that the optical path must be the same for all the rays. So if I take the optical path of the ray from P to R, which is D, this small d, and I add the optical path from R to Q, which is this small d1, but now this is inside a material like glass with refractive index of n. I need to multiply that by n. So this is a useful and important thing to keep in mind. Speed of light changes based on what material it is. So in glass, light travels slower than in air, and the amount it's slowed down is called n, which is the refractive index. You saw this when we talked, when Apratham talked about Snell's law. Okay, so speed of light is C naught divided by n. This is speed in vacuum. Okay, this is our very familiar number, which Einstein told us cannot change, right? But in materials, it can change based on index. Now, so one way to think about this optical path length is based on time. So if I have a photon that leaves this location and travels this way, how much time does it take to go from here to here? Of course, time is speed, distance divided by speed, right? So my distance I have traveled is d, speed is c naught because this is air or vacuum. So that's the time. Goes from P to R. The time going from R to Q is d1, which is the physical distance that the photon travels from here to here, divided by the speed. Now speed, as I told you, is c naught over n, right? Because it's slowed down in the glass. So this is d1 n times c naught. So this is time for the photon to go from P to R to Q is now d over c naught plus d1 times n over c naught. Okay, so that, and then of course I can take the c naught out, so I'll simply get d plus d1 times n. And that's exactly what I have here. And you can do that for all the rays. And what you see, because c naught is constant, everything cancels out, you can see that optical path length optical path length, which is d plus n times d1, is the same for all the rays. Now, if you define this geometrically, you can actually solve this analytically. This defines a surface, defines a locus of points where the rays must all have the same optical path length. And for a point source, for small angles, you'll see this becomes a sphere. Okay, you can actually prove this. But anyway, so that's how that's formed. And this is just a review because, and by the way, this bending happens because of Snell's law, right? Everyone's familiar with that by now. So that's how you get the surface. So that's one point. Now, of course, one point is not very useful. To do imaging, you need at least 2 points, right? Probably more, many more points if you want to design a lens for your iPhone camera, for example, right? So if you have 2 points, you need at least 2 surfaces. You can actually show this. So the 2 surfaces can be designed such that 2 points, in this case, E gets imaged to B and F gets imaged to A. And the key thing to keep in mind is that now we have 2 degrees of design freedom here. And you can show that you need these 2 in order to be able to map 2 points. to 2 points. However, what happens to a point in between? The point in between is no longer mapped to, not necessarily mapped to a particular point in between here, because we actually haven't forced that to happen. And in fact, you can actually show that it's not possible to force that to happen. We won't go into that level of detail. And you can actually, in fact, show that if you want to have perfect imaging, and what I mean by that is that every point of the object, let's say, which is an infinite number of points, you want them to be mapped to the infinite number of points on the image, you need an infinite number of surfaces. So, or a perfect control or refractive index. So this is actually, of course, not possible. So in real life, all real lenses form imperfect images or images of aberrations, which is why, by the way, today, the vast majority of the images that you take, like your selfie and so on, is post-processed by a computer, which tries to make those imperfect images as perfect as possible. Now that's the subject of another completely different class, but I need you to understand this conceptually to talk about non-imaging optics. Now, going one step further, if you think about the lens as a concentrator, okay? Now, we define this two surfaces here, and we are saying, going to call this a lens, okay? And we design this lens such that rays from E end up at B, and rays from F end up at A. And I told you, rays in between can end up anywhere in between. So there's no mapping, no one-to-one mapping. However, you can actually show that if the edge points E and F are imaged onto A and B respectively, as we just said, then all the rays in between, any point in between, these rays have to, of necessity, end up in between A and B as well. So E and F act as bound values, boundaries for all the rays. Now, if you think about it, what has happened is that if my receiver here, AB, is smaller than my source, EF, I have taken light from my source, which is now larger, and shrunk it onto a smaller receiver. I have done some level of geometric concentration. Now my lens is the concentrator, but no image is formed because I cannot guarantee that a point in between has a unique point in between. I cannot guarantee that because I only have two surfaces, okay? Now you're starting to understand the difference between imaging and non-imaging optics. Okay, the fact that I cannot guarantee that there is a point, a one-to-one map for all those points in between means that I'm now in a regime of non-imaging optics. It's not an image formed, but I'm still collecting energy, or I'm concentrating light. Again, there is no one-to-one correspondence between points on the object and those on the receiver. And in a sense, this is a simpler design problem than an imaging optic. Now, let's think about a slightly simpler case where the source is really large and far away, like the sun, okay? So in other words, the source is now infinitely far away from the lens, okay? So instead of having a point, imagine this EF is now really far away. These rays now start becoming parallel to each other, like as shown here. So basically you have a bundle of rays coming at some angle, you have another bundle of rays coming at some other extreme angle, and there are bundles of rays in between, but these are all parallel. Because these are parallel, as they pass through the lens, they get focused to a point at some distance defined by the focal length. And the same thing happens on the other side. This is a completely symmetric with respect to the optical axis, which is this. Parallel rays D1 are focused onto A, parallel rays D2 are focused onto B. And all rays in between, as we just said, will end up between A and B, but they need not be focused to single unique points. Okay. This is essentially the crux of non-imaging optics, and I'm going to end here, but let me just say this one more time. I have an optical system. It doesn't have to be a lens. I drew a lens here, and I have a receiver here. Let's imagine a solar cell. All I'm saying is that if I have rays of light coming into the system at some angle, I ensure that all these rays are focused to one edge of this receiver. And now if I have a different set of rays coming at this angle that is focused to the other edge of the receiver, and if I have any other set of rays in between, can be anything, I cannot guarantee that that will be at a single point, but that I can guarantee that it will end up on the receiver. Okay, so what I have done is I have taken energy from a cone of angles and essentially put them on top of a receiver without forming an image. And this is what a non-imaging optical system does. And of course, a good example would be a solar concentrator. Okay, and at this point, I'll stop and see if there are any questions.